Hi, and this is module 5 for part 8. So for this module, we will be discussing infrared spectroscopy. Okay, so again, please take note of the respective chapters, no, or pages sa textbooks, no, nung topic na ito. Alright, so the infrared region is actually divided into three subregions, no. So you have your sorry. So you have your near IR. So let's erase that. Alright. Yeah. So you have your near IR, your mid IR, and your far IR regions. Okay. So in infrared spectroscopy, you can use each of these regions. Okay. Now, roughly, the near IR region in terms of reciprocal, ito na gamitin natin, no? So per cm, alright, near IR is around 12,820 to 3,333 per cm, or in terms of micrometers, that is around 0.78 to 3 micrometers. Alright, for mid IR, this is around roughly 3,333 up to 200 per cm. Alright, or in terms of micrometers, this is around 3 to 50 micrometers, yeah. And far IR, in terms of per cm, is around 200 to 10 per cm, or that is 50 micrometers to 1,000 micrometers. Okay, now in organic chemistry, no, sa organic chemistry, no, this particular spectra, for example, focuses on mid-infrared spectroscopy. Okay? Yung near IR, application nito is more of quantitative. Okay? Although we will not be discussing this in full detail, our discussion will focus more on the mid-IR spectroscopy. Okay? Yung principle nila pare-pareho. Lahat ito vibrational spectroscopy. Okay, so NIR, this is more for quantitative analysis. Normally, you can use NIR spectroscopy for in situ analysis of products. So usually sa manufacturing setup, no? So one example would be the if you're working in a food company, for example, no, chocolate factory, then you want to measure the percent proteins, percent carbohydrates, percent fats, no, for example, of a given chocolate sample. Traditionally, what you would be doing are separate analysis, no, for each component, no. So for protein, you do Kjeldal. For carbohydrates, maybe you do some Brix analysis or HPLC siguro. For fat analysis, you do exhaustive extraction using Soxlet, and then you weigh, no, yung mare-recover na fats, no. So these are very tedious procedures, no. But nowadays there is an NIR instrument, okay, based on recording, okay, standard samples of chocolates, meaning chocolate samples with known amounts of proteins, fats, and carbohydrates, say, from your conventional standard methods. So you feed that, no, you feed that along with the NIR reading, no, using the instrument, and then a chemometric algorithm will formulate um, a parang equation or model that when you analyze an unknown chocolate sample, you will instantly get the percentages, no, of the analyte, no, na mini-measure yung protein, carbohydrate, and fats, no. So it's a very advantageous, no, na system, although medyo may kamahalan, no. So that's one application of NIR. Mid IR, although you can also use this for quantitative analysis, no, wala namang problema doon. Yung major power nito is more for qualitative. Okay, qualitative analysis, no? Especially for many organic compounds, all right? So organic compounds, polymers, for example, some inorganic compounds, although limited, okay, different macromolecules, no, okay, so andun yung power ng MIR, no? So as you've experienced in the laboratory, basically every sample, every analyte would generate a somehow, no, unique spectra, no, mid IR spectra, no, as such as what is presented here, no. This is what butanal, no. So butanal, all right, will exhibit this particular set of peaks, okay, and each peak is characterized by the intensity, yung strength, no. So sometimes based on intensity, ito yung sasabi natin strong intensity, di ba? Mid intensity, no, mid strength intensity, or weak yung intensity ng peak. Also, important characteristic is the wave number, no? Saang wave number tumama, okay, yung bawat peak, no? And we know that each wave number, all right, designated for a peak corresponds to a particular vibrational mode, okay, which is unique for a given molecule, given that they have their own sets of molecular bonds. All right. What else? Also, the peak shape will give you information, no, about the identity of the particular molecular bond or functional group being represented by a peak, no. So for example, this one, no, we refer to this as a sharp peak, no. And for carbonyl, no, this is one of the more readily recognizable peaks, no. So carbonyl stretch, okay, is recognized as a sharp, strong peak. All right. If you remember yung OH, no, for OH, diba, broad, no. So meron ka namang broad peak, no. Yeah, so intensity of the peak, peak position, peak shape will give you information, okay, regarding doon sa functional group or type of molecular bond present, no. So this is mid IR. For quantitative analysis, usually what we measure is the peak intensity. All right, the peak intensity, we just select a particular peak, okay. For this given spectra, no, usually for IR spectra, we represent the y-axis in terms of transmittance. But there is no problem if this is represented as absorbance. Okay lang yun. Ang mangyayari lang, magiging pabaligtad yung peaks, no? So what you can do for quantitative analysis is you measure the intensity of a strong peak, all right. Since this is transmittance, you have to convert the transmittance value into absorbance, no. And since this is absorption, no, infrared is actually absorption spectroscopy, the absorbance corresponding to a peak is also proportional to the concentration of your analyte. Now, it will also follow Beer-Lambert's law. All right. Then lastly, you have your far infrared region. This is more for qualitative analysis, particularly for inorganics. Okay, inorganics. Okay, so if you're analyzing like mineral samples or geological samples, you can um, identify, all right, or get the spectroscopic fingerprint for that particular sample using far infrared radiation. Okay, so the focus of our discussion will be on mid IR. The x-axis is usually represented in terms of wave number. Medyo historical lang yung reason for that. All right. But what you have to recognize is that the wave number is simply the reciprocal of your wavelength. All right. And the reciprocal of the wavelength is, of course, directly proportional to what? To the frequency of the radiation, and hence the energy of the radiation, no. So if mapapansin from 4,000 to say 400, okay, you are actually going towards longer wavelength. So longer wavelength meaning you are going towards lower energy level, no? And this is analogous to your UV spectra. Diba? Remember, from left to right, for your UV spectra in terms of wavelength nanometers, increasing din yung wavelength, yun yung convention natin. Okay? So basically, the different vibrational modes available for a given molecule are your stretching vibrations and your bending vibrations. No? So for stretching vibrations, you have your symmetric stretch and asymmetric stretch. Whereas for bending vibrations, you have yung tinatawag na scissoring, wagging, no, in plane, no, in plane ba ito? Yeah, no, and then you have your rocking or in plane wagging, and your twisting or out of plane wagging. Okay, now in general, stretching vibrations are induced at higher energy levels, no? So higher energy level, higher wave number values. Whereas most bending vibrations can be found at the lower end, no? Lower wave number values, okay? Now for a given molecule, the amount of infrared radiation or amount of energy from the infrared radiation needed to induce each vibrational mode depends on the type of bond present in your molecule. Okay? So if you remember, no, IR is actually, no, yung theory nito is related to your Hooke's law. Hooke's law. All right? So nasasabi ni Hooke's law, yung frequency, all right, of the inducing, no, the frequency that you need to be inducing, no, between a given spring, no. So yung theory niya kasi, or the way we imagine molecules, that you have two masses connected by a spring. Okay, so to induce vibration, okay, between the spring, no, along the spring, correspond to a certain value of frequency. All right, may two factors that affects this, no. You have your spring constant, or tawagin natin itong parang strength ng spring. Since we are talking about molecular bonds, K is related to your bond strength. All right, and also related to your the masses, no, of the two, yung dalawang magkakabit, no, na atoms, no, in this case. All right, so this is related to mu. Well, sa original Hooke's law kasi, the masses are represented by your, ang tawag sa mu, your parang combined mass, no. So ito yung parang combined mass, no. So this is the sabihin natin yung mass ng atoms na nakabit. At anong sabi sa Hooke's law, no? The frequency, all right, is proportional to the square root of the bond strength over the masses, no? The mass ng atom. So ano ibig sabihin nan? So remember, frequency is directly proportional to your wave number. So let's use your wave number. So in terms of bond strength, ano sabi dito? Directly proportional sa square root ng bond strength. And in terms of the mass, mu, the wave number, okay, is directly proportional to the inverse of the square root of your mass, no? Yung atom mass. And makikita natin ito sa pag-aaral ng infrared spectroscopy, no? So for example, no, in terms of different or varying atomic masses, so let's look at different types of carbon bonds, no? Or sorry, carbon to atom bonds. So you have yung carbon hydrogen, you have yung carbon deuterium, and you have your carbon carbon. All right, so alam natin, no, just by looking at these examples, that the trend, no, nung masses nung atoms na nakakabit dito sa particular carbon na ito is actually, as you go down, increasing, no, increasing atomic mass. Okay? Now, if you look at your IR tables, okay, yung wave number values nila would be roughly 1,200. Sorry. Mali. This is 3,000. You have 2,100 and 1,200. So, makikita natin. As you increase the atomic mass, what happens to the wave number? You have a decreasing trend in the wave number, no, which follows this particular trend, no, or relationship. Okay. Now, in terms of bond strength, so let's erase this. All right. Medyo hassle na magbura dito. Anyway. All right. So, in terms of bond strength, K, no? So, anong gagawin natin? Different carbon ba? So, carbon single carbon, carbon double carbon, and yung carbon triple bond carbon, no? So, here, the trend now is in terms of increasing bond strength. Okay? Alam natin, mas stronger yung bond, no, as you increase the degree of unsaturation. Now, in terms of the wave number, so if we look at your tables, no, so CC is 1,000. C single bond C 1,200, 1,660 roughly, and 2,200. So we can see that the trend is now towards increasing wave number values. Nakuha, okay? So basically this is the general relationship, no, ng bond strength and ng atomic mass doon sa wave number for a particular vibrational mode. Okay, so this is your generic IR spectra. So nasabi natin kanina, no, the x-axis is your wave number usually in per cm, and the y-axis is usually in terms of transmittance or percent transmittance, but this can also be in terms of absorbance, no, walang pinagkaiba yun, magbabaligtad nga lang yung itsura nung IR nyo, ng IR spectra. Now, yung region between 4,000 to roughly around 1,600 shows you the strong signals, no, the strong peaks, usually corresponding to strong stretching signals. And you call this region of the spectra your diagnostic region. Okay? Whereas the region down below, no, 1,400 towards 200 or 600, this is what you refer to as your fingerprint region. Alright? So, the finer signals, okay? Finer signals, no, which is, basically more unique, no, for a given analyte or sample, can be seen in this region. And normally, this region corresponds to the weaker stretching vibrations and most of the bending vibrations. So when you want to interpret an IR spectra, ang trick doon is you first look at the diagnostic region, all right, and identify which which of these following functional groups, no, could be present in your sample, no, before you look at the fingerprint region. Yung fingerprint region medyo mas mahirap itong i-decipher. Alright, no? Medyo mas mahirap ito kasi nga medyo mas magugulo yung signal dito, no? Whereas for diagnostic kasi usually mas malinis yung appearance ng peak. When you say mas malinis, you have fewer peaks, no, in the diagnostic region compared to your fingerprint region. Alright, so later on, I'll show you a trick on how to determine or how to interpret your IR spectra. Alright, so the modern infrared spectrometer is actually based on Fourier transform infrared spectrometer. So this is a non-dispersive instrument, meaning it doesn't contain a monochromator. Okay, so instead of a monochromator, it uses what you call a Michelson interferometer. no? So symmetrical interferometer basically it's just a combination of a fixed mirror and a moving mirror. All right, so this enables us to simultaneously collect data across the wavelength range or the wave number range of interest. Okay, so wala ka na ditong gratings or prisms. Okay, so ang advantage nito, so i-run down natin, no? So ang advantages nito, no, against dun sa sinauna, wala na actually yun, no, yung dispersive IR, is that of course it has better sensitivity thanks in part to its detector. Okay, the detector used for FTIR is hindi na siya based doon sa yung thermocouple, thermistor sa bolometer, no? Hindi na ginagamit yun ngayon, no? So it's either a pyroelectric device, okay, such as your deuterated L-alanine dope triglycine sulfate, or it can be based on your photoconductive detectors, all right, such as your, for example nun, your lead sulfide, or your yung mas common, mercury cadmium telluride, no? So these are mga ceramic, no, materials, all right. It uses less energy from the source, no? So there is less another way of saying this is that it has lesser attenuation, no, from the attenuation of the energy or the power or intensity of the incident radiation, no? So nasabi na natin before, no, that the more the less attenuated, no, or pag mas konti yung mga elements na bumabawas doon sa energy ng incident radiation, this leads to better sensitivity. And why is this? Because you have lesser optical components inside the IR. Wala ka na yung, kasi yung grating na yan, prism na yan, it really attenuates, no, yung energy or yung intensity ng incident light. Alright, so this leads to better sensitivity. Okay, this is one of the advantage. Yung dispersive dispersive instrument kasi na IR nung araw, to get a single scan, it will take you around 1 to 2 hours, no, before you can get the whole spectra. And this is because of the lower sensitivity of the detectors. Kasi remember, if you have a dispersive type monochromator, no, yung movement, no, of the monochromator element, dispersive element, kada galawnan saka ka palang tatama doon sa particular wavelength or wave number na gusto mo i-measure yung transmittance or absorbance. And since mababa ang sensitivity ng detector mo, kailangan matagal mong i-expose, no, yung detector mo towards that particular wave number before you move to the next wave number value, no? So yun yung nagpapahaba sa analysis. Now since here you just have an interferometer that enables you to collect all the data at once, no, 1 to 2 seconds lang kuha mo na yung isang scan. And anong advantage nito? If you are able to get a complete scan in a fraction of a time, what the instrument does is that it usually collects more scans, no, usually 10 to 20 scans, no, or you can even do 50 scans kung trip mo. Alright, and all of the scans are now averaged. Okay, so when you average these repeated scans, you are increasing the signal to noise ratio and hence increasing the sensitivity of the analysis. Okay, so yung number of scans that you do depends on the level of signal to noise ratio that you want to get, no. However, isang disadvantage nun is kung importante sa iyo yung mga weak signals ng sample sa IR spectra, usually yun nawawala yun, no, or lumiliit lalo yun, no, after averaging. Alright, so kung importante sa iyo, you need to lessen the number of scans, no, para hindi ganoong mawala or masyadong ma-attenuate yung intensity ng mga small peaks na iyon. Alright, ito masasabi natin, no? So again, you take several scans and you average, no? By the way, no, light source, no, for an FTIR is usually a ceramic light source, no? Usually silicon carbide. Okay? Pwede rin naman yata tungsten, no? But usually silicon carbide yung ginagamit. Okay? Now, one problem sa IR, sa FTIR, is that since wala kang monochromator, there is no way for you to discriminate between the wave number or wavelength values nung nanggagaling sa IR source. Okay? So, to circumvent that problem, FTIR instruments is also equipped with a laser. Alright? So, the laser serves as your wavelength standard or wavelength reference. So, yung laser has a constant wavelength, no? So, usually, helium neon laser yung ginagamit. So, around, mga around 760 nanometers yata, no? Pakicheck ka lang sa textbooks. Yung wavelength, no? For a helium neon laser. So, since ito constant, okay? Yung computer na, yung nag-a-assign noong wave number values for the spectra generated, no, nitong instrument, no? So pinepeg niya or binebase niya yung assignment ng wavelength values doon sa constant wavelength value ng laser source. All right? Okay. And ayun nga sasabi natin, no? So you have a laser beam, no, that keeps the instrument accurately calibrated, no, in terms of your wavelength and also the alignment of the optics, no? So kahit ng optical instrument, importante that you are able to keep the alignment, no, of all your optical components, no? Kaya nga isang importanteng bagay, no, when you're installing your optical instrument, whether that is UVVs or AES or IR, is that dapat nasa stable siyang lalagyan, no, malayo sa any source of vibration, no, because this can actually misalign the optical components inside your spectrometers. Okay? Now, ang FTIR is a very powerful instrument because you are this will enable you to analyze a wide range or variety of samples, no? Pwedeng solid, liquids, gases, slurry, sludges. Okay? So napakalawak, no, nung iyong pagpipilian. However, ang disadvantage lang siguro is number one, ang FTIR spectrometers ay susceptible sa carbon dioxide. Okay? So if you have too much carbon dioxide doon sa atmosphere or doon sa sample compartment, pwedeng masapa kasi IR active yun eh, no, yung peaks nun, very strong. So pwede niya masapawan yung peaks mismo ng sample mo. And also water, no? Water is a no-no when it comes to FTIR. Bakit? Dalawang bagay, no? Una, water kasi malakas ang signal ng water sa IR spectroscopy. So mangyayari doon, masasapawan lang yung signal. Okay? In my experience, even if you do background correction, no? Kunwari, gusto mo mag-attempt ng kung trip mo, no, aqueous sample, no? And then gagawin mo parang sa UVBs, no? You mag-run ka ng blank na water, i-background i-run mo siya as background. So basically gagawin ng instrument, ika-cancel na yung reading ng water, no? Kaso since very strong ang reading ng water mo, ng background mo, pag nilagay mo yung sample mo na may analyte dissolved in water, water pa rin yung mababasa ng instrument. Alright, so no ang water. Okay, water and carbon dioxide. And another reason why ayaw mo ng water is that, remember, the optical materials used for a given instrument should be, sabi nga natin, invisible towards the EMR region that you are using. And since infrared ito, alright, you cannot use here glass or quartz, because glass, quartz, or even plastic, of course, can absorb infrared radiation. So yung mga mirrors dito, mga beam splitter, mga lenses are made from salts, no? So mga salt window, KBr, sodium chloride. So if you have water present, it will corrode, no? Or siguro pinakamadaling explanation, it will dissolve away, no, your salt window. So no ang water. Okay? And isang another important na kailangan maalala sa FTIR spectrometers is that sensitive ito sa relative humidity ng kwarto. Kaya nga usually if you have an FTIR instrument sa lab ninyo, naka-separate na room. Alright, yung FTIR, no, usually may 24 hours na aircon. Okay? And then meron kang control sa relative humidity. Okay? Importante na non-condensing and not greater than I think 70% RH, no? You can also double check, no? Pero mga around that value yan. All right? So if you exceed that value, okay, mako-corrode yung mga lenses and mirrors mo, no, sa iyong instrument. Usually, no, most FTIR instruments are equipped with internal desiccators with indicators din, no? So, yung desiccators na yun ay pinapalitan after magpalit ng kulay yung indicator. Alright? So, consumable yun, no? Ang IR source, yung light source, this will usually last you around 2 to 5 years, no? Depende sa usage. Yung laser source, ganun din, no? Around 2 to 5 years. Mag-a-alarm na mag-notify naman yung instrument kung kailangan ng palitan. Okay? Ayan. So, this is your FTIR spectrometer. Okay. So, basically, for IR spectroscopy, there are two ways, no, to analyze your sample. No, it can either be via transmission or via reflectance. No, so transmittance measurement or reflectance measurement. All right. So, this uses different sampling accessories, no? So yung pagpili ng appropriate sampling accessory would depend on the sample type, no? Number one, sample type, kung solid, liquid, gas, or slurry. Okay, is it too opaque? Alright, sometimes if your sample is too opaque, transmission or transmittance measurement is not adequate, no? So you can use reflectance. So well, may pros and cons lang naman ito, no? Yung paggamit ng transmittance or reflectance measurements. But basically, transmittance measurements yung pinaka gold standard ba? No, in IR spectroscopy. Alright? Kasi yung transmittance measurements, no, ito yung mayroong direct relationship with absorbance, no? So if importante sa iyo yung quantitative measurements, okay, then you have to use transmittance or transmission techniques. All right, so yung una, all right, na transmission techniques would be your KBR pelletization. So basically here what you do is you mix grounded KBR salt, no, dried KBR salt with your analyte sample. Usually ang ratio ginagamit is roughly 1:10, no, 1 part ng analyte to 10 parts ng KBR. Alright, you grind your sample, no, with the KBR, and then you place it in this die press ang tawag dito, no? So the die press is placed on the tawag dito, placed on the hydraulic press. Alright, so mag-a-apply ka ng pressure. Alright, mag-a-apply ka ng pressure, and the result will be a crystal, no, a clear, no, ideally, no, it should be a clear, or kung di man siya sobrang clear, kailangan translucent, no, kasi pag sobrang opaque yung crystal mo, hindi makakatawid yung infrared radiation, no, so magiging masyadong mataas, no, yung transmittance mo. So ayaw mo yun, no? You want ideally, no, pag transmission, ang highest transmittance value ng peak should be around 60%. Alright? So kailangan walang butas, no, yung crystal mo. No, kasi pag may butas yan, makikita mo yung baseline ng IR will not be 100%. It will be higher. No? Kasi may nakakalusot na ilaw na hindi nag-i-interact with your sample. So basically here, after forming the crystal, meron kang apparatus, no, doon sa loob ng sampling chamber mo. Let's have the pen. Alright. No, sa sampling chamber mo, so kung ito yung light source uli, saka yung detector mo, alright, yung crystal ay nilalagay sa gitna, no, para dito dadaan yung infrared. Kaya siya talaga transmission technique, no. So KBR is used, or even sodium chloride, no, anhydrous sodium chloride can also be used. Okay, so saan ginagamit ang KBR pelletization? No, usually this is for solids. Okay, solids na hindi hygroscopic and can be molded into a pellet. Okay, yan. So next, you have your sealed liquid cell. So ito yung assembly ng sealed liquid cell natin. Well, ginagamit ito of course, no, for liquid samples. Again, walang water, no? At bakit walang water? Kasi yung assembly nito, yung cell window na tinatawag, these are salt windows, no? Also made from either KBR, sodium chloride, or whatever salt yung ginagamit. So when you assemble this, no? So ayan, pag na-assemble mo yan, okay, yung tawag dito, itong mga plugs na ito, dito mo i-inject yung liquid sample. So pag i-inject mo yung liquid sample dyan, itong space na ito will be filled with your liquid sample, and since KBR naman yung window mo, pag tumawid yung ilaw dyan, no, you can measure the resulting transmittance. Okay, so aside from pure liquids, you can also analyze using the sealed liquid cell solid samples, no, dissolved in appropriate organic solvents. Ang trick lang is kailangan yung organic solvent mo is medyo invisible towards IR radiation, no? Kung ito medyo invisible, hindi ba ibig sabihin completely walang peaks, no? Usually meron siyang isa o dalawang peak na hindi nag-overlap, no? Ideally doon sa IR spectra ng analyte mong naka-dissolve or naka-dispersed doon sa solvent na yun. So common solvents na ginagamit would be your carbon disulfide, carbon tetrachloride, no? So these are highly symmetric organic molecules, no? Ang problema nga lang sa kanila, no, if you're familiar with these chemicals, is that they are carcinogenic, no? So yun yung main limitation nila. Okay, you can also analyze gases. Okay, so this is a gas cell, no? So basically you have your stopcocks. So you using a pump or a syringe, you fill this up, no, with the gas sample. Okay, then you lock the stopcocks. Okay, so the gas are trapped dito sa, well, glass cylinder lang naman ito. Pero doon sa magkabilang ends is you have also your KBR windows or sodium chloride windows. So yung ilaw dito magpa-pass through. Alright, so again, may accessory yan sa loob ng FTIR na ipapatong mo lang ito, and you can measure now the IR spectra for gases. Okay, so pag sabing transmission techniques, yung infrared tumatawid sa mismong sample natin. Next, you have your reflectance technique. Now for the reflectance technique, basically what you do is that you allow, so this is your sample, so you allow your infrared radiation, alright, to bounce off, okay, from your sample. Okay, now during this reflection process, some of the energy of the incident radiation is absorbed by your sample, no? So that it means to say that the energy of the incident, well, we expect that this would be attenuated, no? So this would be greater than the energy of the reflected radiation. Alright, now here you measure the amount of the reflected radiation, so you call that term reflectance, no? So analogous to your absorbance and transmittance. However, if you want to quantify or relate this with weird numbers though, you need to express this in terms of absorbance. Okay, so well, not to worry, no, because your reflectance, okay, is actually related to your absorbance, no, via the so-called Kubelka-Munk Kubelka-Munk equation. Alright, so just research this, no? Para may gagawin naman kayo no, sa textbooks or sa internet. So, Kubelka-Munk equation, so this relates reflectance to absorbance. Alright, now in general, there are two well-known reflectance techniques. The first one is your diffused reflectance. Alright, so this is for powdered samples, no, solid samples, powdered samples, or samples that can be pulverized. Okay, so here what you do is you mix your pulverized sample with KBR. Okay, well, the ratio is also 1:10, but this time you don't need to pelletize the mixture. No, all you have to do is you need just to place the powder onto this sample cup. No, itong part na ito, no, ito yung sample cup. Alright, now the trick here is to ensure that you evenly and level you evenly place your powdered sample onto the sample cup, and make sure to level, no, so kung ito yung sample cup mo, kailangan pantay yung level ng powder doon sa rim ng sample cup, no, so your infrared radiation will bounce off, no, doon sa sample mo. Okay, so you have these lenses here, all right, no, collimating mirrors rather, okay, that will focus the incoming IR radiation and the reflected IR radiation, no, towards the detector. Okay, yeah. Then next, you have your attenuated total reflectance. So instead of using KBR or powder sample, we make use of crystals. Alright, so the crystal can either be made from zinc selenide, germanium, alright, or even synthetic diamond. Of course, this is more expensive, but the advantage of your diamond is that it's sturdier, no, compared to these two, no, because these two can break, okay, pag masyado mataas yung pressure. Now, if you can analyze solids and liquids, no, using ATR. Alright, kung liquids yan, you just drop, okay, some of your samples. Of course, wala pa rin water, no, kasi masyadong overwhelming yung signal ng water. Okay, then you just run your IR. Okay, so the principle here is based on attenuated total reflectance, wherein in the absence of the sample, infrared radiation, okay, will repeatedly, no, depende dun sa type of crystal, this is a multiple bounce type, no, but there is also a single bounce type na tinatawag, no, yung sa Adamson na lab is a single bounce type, no, so meron ka ng isang circular na crystal. For multiple bounce, you have a rectangular crystal, no, so basically the principle here is that in the absence of the sample, the IR source na galing sa ilalim yon, it will bounce off, okay, without attenuation, okay, dun sa crystal, no, sa loob ng crystal. Alright, now in the presence of the sample, some of the infrared radiation will actually penetrate the crystal before bouncing back inside, okay, so the depth of penetration is around 0.25 microns. That is why ATR is considered as a surface technique, okay, because if you have a non-homogeneous sample, basically the IR spectra that you're collecting is just for the immediate surface, no, the one that is nearest the crystal. This is the reason why you need this pressure head here. Alright, you need to apply some degree of pressure onto your solid sample so that the sample is well in contact, no, with the crystal. Lapat na lapat dapat yung solid sample, no, dun sa yung crystal. Okay. Another thing to remember is that for different crystal types, okay, meron niyang cut-off. Alright, so for zinc selenide, the cut-off is around, well, roughly, no, 700 per cm, whereas for diamond, this is roughly around 525 per cm. Meaning to say, if you're going to run your IR towards lower wave numbers, alright, beyond the cutoff, you will be reading already the signal for the crystals, no, themselves. Alright, so you need to be mindful doon sa kanilang cutoff values. Okay, so some tips in interpreting your IR. Alright, you don't need to memorize, no, the very long IR table. Okay, ano yung kailangan maalala dito? Again, no, to reiterate, information sa IR is based on sa number 1, yung peak position, no, yung wave number corresponding to the peak, the intensity of the peak, ano ba yan? Strong intensity, mid intensity, or weak yung intensity ng peaks, and also the peak shape, no, whether it is sharp or broad. Alright, so shown here are the so-called base values, alright, for the different common functional groups. So you have OH, NH, no, NH can be found in amines and amides. Alright, now both OH and NH usually exhibit broad peaks, no. In the case of amines or amides, for primary amines, no, you will have a broad peak with 2 sharp spikes, but for secondary amines or amides, it's a broad peak with 1 sharp spike. Alright, ayan. But if you have a tertiary amine, you won't have any broad peak, no, at 3400, because this corresponds to the nitrogen-hydrogen bond. Okay, so kung wala yung hydrogen, you don't expect peaks, no, coming at this wave number. And of course, you have your CH bond. Okay, you have your C triple bond C and C triple bond N. Ito, madali lang ito, no? What you can do here is that if you have your spectra, and this both of these are weak intensity peaks, no? So, ang technique, kung may nakita kong weak intensity peak sa region na yan, you draw a line at around 2,200, no? Pag nasa kaliwa yung peak, then that is alkyne, no? Pagka nasa pag nasa kaliwa yung peak, that is alkyne. Pag nasa kanan yung peak, that would be a nitride. Alright, then you have your carbonyl peak. Okay, base value 1715. Now these base values, no, this will shift either towards the left or the right depending on the type of functional group that owns the particular signal. No, so for example, carbonyl is found in a variety of functional groups, no? You can have a ketone, you can have an aldehyde, an ester, an amide, a carboxylic acid. Alright, so yung base value to will shift. Alright, so for example, no, the 1715 value is usually associated with a ketone. Okay, now if your carbonyl is an aldehyde, or part of an aldehyde, expect that the carbonyl peak, no, the strong sharp peak, will appear at a higher wave number value, no. But if you have an amide, alright, then the carbonyl will be found at a lower wave number value, so around 1600s na, no, ganun kababa. Okay, and this is because of well, in general, bond lengthening. Alright, so if the base value goes to a lower wave number, it means to say that the particular functional group induces a longer bond, no, doon sa particular signal na mini-measure natin sa carbonyl. Okay, so yeah, so you have carbon double bond carbon at around 1650 and carbon single bond oxygen around 1100. Okay, and if you notice, no, isang sikat na signal is yung for esters, no. For esters, the carbon oxygen bond will be found at around 1200. So why is that? Okay, for ethers, so yan, no? For ethers, all right, since you don't have a carbonyl bond, no, the bond length between the carbon and oxygen is a little bit longer. So that's why makikita mo siya sa lower wave numbers, no? Whereas for an ester, all right, the presence of the carbonyl draws your electrons, no, towards the carbonyl carbon, shortening the carbon single bond oxygen bond. So that's why you tend to find this signal at a higher wave number. Alright, what else? Hydrogen bonding and dimerization shifts the base peaks to a lower wave number. So one example of that would be your carboxylic acid, no? If you have an alcohol, no, the OH corresponding to an alcohol can be found at a higher wave number, around 3600. But if you have OH attached to a carbonate or carboxylic acid, this particular signal will now appear at a lower wave number, no, around 3200, which usually overlaps with the C single bond H signal. Alright, so well, it's good to memorize, no, or to be at least familiar with this range of values. Okay, so a good way to interpret your IR is by doing deductive reasoning. Okay, sa IR spectroscopy kasi, the absence of a peak corresponds to the absence of a particular functional group. So it's easier to look for missing peaks rather than interpreting the peaks present. No, mas simple yan. Okay, so how do we do deductive reasoning, no, in IR interpretation? So normally for the board exam, they will just give you the IR spec of a pure organic compound, no? So mas lesser yung complexity ng problem, no, compared to real world problems, no, wherein normally you analyze mixtures, no. Pag mixtures ang ina-analyze sa real world, no, real world, sa work scenario, normally what you do is you just compare it with the standard products. So kunwari, issue on counterfeiting ng paint products, for example. Okay, so again, alam natin na IR is useful for generating a chemical fingerprint, okay, for a particular sample. So if you have a standard ng product mo na paint, you run the IR, so you get the spectra. Then yung product na nasa market na sasabi natin counterfeit, you run yung IR ulit. Okay, if the IR spectra for the sample is different from your standard, then we say na you have a counterfeit product, no, evidence yun. Kasi chemical fingerprint mga IR. Okay, but for the board exam, usually pure compounds. Okay, so una mong hanapin, carbonyl peak, no? So alam natin carbonyl peak is a strong sharp peak at around 1700s. Okay, pag meron, ibig sabihin ano yung choices natin. Kung meron kang carbonyl peak, ibig sabihin the unknown is a carbonyl derivative. Okay, so it can be a ketone, an aldehyde, an ester, a carboxylic acid, a carboxylic anhydride, alright, amides. Okay, so yun yung choices mo. So anong gagawin? You look for the other signals, no? So kung carboxylic acid, aside from a carbonyl, you need to find a broad absorption peak at around 3,300 that usually overlaps with CH. So that's indicative of carboxylic acid. Okay, if you expect an ester, then look for a strong intensity peak then at around 1300 or 1200, and that will give you the C single band O stretching. Okay, so in combination nun with the carbonyl, alright, indicates that indeed you have an ester. If wala lahat yung mga features na ito and may carbonyl ka, then basically you have a ketone. Alright, so napakadali lang nung technique. Alright, deductive lang. Now, what if wala kang carbonyl? So kung wala kang carbonyl, then all of these are impossible, no, choices doon sa iyong problem. Alright, so kung wala kang carbonyl, then may mga choices, no? So it can be this yung walang carbonyl na functional groups. So alcohols, amines, ethers, unsaturateds, no? Yung mga boring na molecules, no? So for those na walang carbonyl, then you can have mga heteroatomic, no? So kung meron kang broad adsorption peak at 3,400, then you might have an alcohol. Okay, for amines, no, you look for medium absorption near to the 3,400. If you have ethers, then you expect strong signals, alright, at around 1300 to 1000 per cm. Okay, for double bonds and aromatic rings, no, so you have the following signals. Okay, kung carbonyl derivative yan, so aside from the 1700 strong intensity peak, you would also look for these particular signals, especially for aromatic. Yung aromatic, hindi rin makita yan. Especially in presence ng overtones. No? Yung overtones, yung parang tatlong kambal na peaks, no? With weak intensity peaks. Usually can be found a little bit above 1800s. No? Those na makikita usually. So it's indicative of aromatic rings. And then of course, you have those na triple bonds. Alright, so yung nitrile saka yung ang tawag ito, acetylene groups, no? Nakita natin kanina how to distinguish. Nitro groups, well, medyo bihirang ibigay yan sa board, no? Sa experience namin. And then if wala ka talagang kahit anong features, then you might have a hydrocarbon. Alright? So let's try yung problem sets natin. Alright, so for this part, try to pause the video. Okay, then determine which of the following choices corresponds to sa IR spectra given below. Alright, so if you chose the terminal alkyne, alright, then this is the correct answer. So, bakit, no? Kasi again, ano yung sabi natin, no? So you have this peak here, alright, which corresponds to your C triple bond C. So kung C triple bond C yan, then of course wala na ito, no? Cancelled na yan. Okay, so pagpipilian lang natin isang terminal alkyne or an internal alkyne, no? So how to distinguish between the two? Terminal alkyne will show yung peak for a carbon-hydrogen bond wherein the carbon is a sp hybridized, and ito yung peak na yun, no, higher than 3000. So this peak actually corresponds to a hydrogen attached to an sp hybridized carbon, no? So kung internal alkyne yan like this one, okay, wala ito dapat. Alright, so this is your terminal alkyne. Okay, so try this one also. So again, pause the video, okay, and try to answer, try to find the most suitable compound, no, for this IR spectra. Alright, so if you chose the ester, then this is correct, no? So lahat ito merong carbonyl functional groups, no? So ayan, meron tayo strong, sharp peak corresponding to a carbonyl. Now, bakit hindi carboxylic? Kasi you don't have the broad peak at around this area, no? Around 3,400. Bakit hindi aldehyde? No? Hindi siya aldehyde kasi ang aldehyde may isa pang peak dito, no? At around 2,800, no? May medium intensity peak ka dyan. This is an ester because you have this strong peak at around 1,200. Okay? And kung mapapansin, medyo shifted ng konti, no? Yung ating carbonyl peak, no? If this is a ketone, no, which it is not, dapat wala itong peak na ito sa 1,200. No? So this is an ester. So that's it for module 5. So again, I'll be posting additional supplementary problems in our Facebook group.